Okay, good evening, everyone. So I'm going to turn on the video just for a little bit. See if I can do that. Okay, so you have this file available in Sakai if you want to get it. I'm sorry, I'm just putting the file, but if you want, you can, hopefully you can find a word opener to do that. Okay, so today I have two things in my mind. One is to cover some things about the graph. We will continue to discuss that. And also, I will talk about the test, which is coming up on April 5th. That's Sunday, I believe. And we'll just go and recall some of the things that, some of the concepts from the test. Okay. So can you guys hear me? Can someone type yes or no? Okay, thank you. All right, so learning goals for graphs are going to be able to graph data structure. You have to define what a graph is. Unfortunately, I don't think I can open up my video, so I'm just going to close that. 1 second here. Okay. So be able to describe how to represent directed or undirected graphs, and be able to estimate the memory required for, like, how much, when you implement a graph, how much memory is required to store the graph. And then more importantly, talk about the applications of the graph. And we will also talk about how to traverse a graph. 1 second, give me a second, because it looks like I broke my connection here. Oh, I'm going to put you, oops, looks like my, okay, there. Okay, great. So let's just go without the video. I don't think that's going to be important anyway. So the definition of a graph. Definition of a graph is that we have, well, vertices called, all right, we talk, and so the graph, when you define a graph, is defined as a set of edges. Fairly slow, my video here. Okay, can you guys still hear me? Hello? Okay, I'm back. Can you guys hear me now? Ah, thank you. Yeah. All right, so let's continue. I apologize for the connection. So we started defining a graph as a set of vertices and set of edges. And so then the next thing that we need to talk about is essentially representing a graph using what we call an adjacency matrix. So if you have a graph here, so the one way to think about this graph, so you might ask, how do you represent this graph on a computer? You can represent this graph as pairs. It says there's an edge from 1 to 2, and also there's an edge from 2 to 3, and 3 to 2, and there's an edge from so on. Read that as a, so if you want this as a set, we can complete that as a set, so you can read the graph into a computer. Now, when you read the graph into a computer, you can store that in a matrix. In a matrix, say this matrix, if there are n vertices, this matrix is n size. The size of the matrix is n squared. Now, if you notice the elements that are true, let's call it 1, that are in the places like, for example, 1 to 2 would be 1. That means it's true. And 1 to 3 would be true, and so on. So we have those elements that are 1, and element 0 means it's false. That means it's not there. Now, so what really, we can have a Boolean matrix. That means they are true or false of n by n to hold this matrix. So the memory requirement is n squared. Now, times whatever the size of a cell, right? So it'd be, if an integer, it would be 4. All right. Now, if the nice thing about the matrix representation is that if you want to find out if there's an edge from I to j. Okay, someone's saying I'm cutting out. Still choppy. Okay. Give me a second. I'm going to restart my computer, okay? Today is not a good day for sure. Hold on. I'm going to restart my machine here. I'll be back in a minute or two. All right. Can you hear me well now? Okay, great. Hopefully changing Wi-Fi network helped. Okay, I'm definitely not using McDonald's Wi-Fi. Someone wrote that on the chat room here. I'm home. It's just my home Wi-Fi is now working right. Okay, I think where we were before this was the fact that we were going to talk about we are talking about the matrix representation of a graph and the memory required for storing this matrix is n squared. Because if you have n vertices, then you would need an n by n matrix. Okay, and then we can ask the question, how do you know there's some kind of an edge exist? All right, so suppose someone asks, is there an edge ij in this graph? Now, once again, I'm going to write this graph can be represented as pairs of points. 1, 2 means there's an edge from 1 to 2. There's an edge from 1 to 3, so you could write 1, 3. So you might imagine that when you input the graph into a computer, you would provide a set of pairs. And then you can see. Now the question is, how do you check whether in this representation the edge ij exists? Can you type something into the chat if someone knows the answer? Okay, so the question is, given, how do we know if an edge ij exists? Correct. So you're asking the question, does ij equals to 1? What is the big O of checking that? Big O of 1, that's correct. Because if you have ij, you can just go to that location. So ith row and jth column. So you can check, you can go to, because all you have to do is, if this matrix is called A, you can look to see if aij is not equal to 0. We can ask that question. That question only requires a constant time operation for that. Okay, now I think the problem with this approach that we are talking about here is that a lot of space is going to be wasted. So a lot of space is going to be wasted. Space is wasted because there are only, if you look at this matrix, we have 5 rows and 5 columns. So we have 25 spaces, but only 1, 2, 3, 4, 5, 6, 7 are used. So only 7 are used. 3, 4, 5, 6, 7. So only 7 are used and 25 spaces. We call these type of matrices sparse matrices. They're called sparse matrices. Now, so we are going to look for a better way to store a matrix. How do we do that? So that takes us to the idea called adjacency list. So if you store this matrix using the adjacency list, essentially what you have is an array of, let's say, 5 places. That's the number of vertices in this list. And then we put whoever is connected to 1. We know 3 is connected to 1, 4 is connected to 1, or 2 is connected to 1. In other words, there's an edge from 1 to 3, 1 to 4, and then 1 to 2. So that means you're going to put those things here. Now, there's no order of the edges, although if you want, you can order them, but there's no need to order that list. So the structure structure that you see here is an array of linked list. An array of linked list. An array of linked list. Now, let's ask the question about the memory requirement for this array. Okay, so we have two structures here. We have an array, and then you have a bunch of linked lists. Okay, how much space the array is needed? Let's assume that the number of vertices is given by n. Number of edges is given by e. So how much memory do we need to store the array? We need memory in the order of n, because that's the size of that. Now the linked list has nodes. How many nodes we need to store? How many nodes are in that linked list? So we said that the number of nodes is e. So in the linked list, we have n nodes. So that means we have order of e edges. Okay, so e total nodes. So the total memory required is in the order of n plus e. N plus e. And we call it on or e because it could be a multiple of n, like 4n or 8n or something like that. Now, this is not a hash table. This could be just an array. It's an array from, if you have 5 nodes, then you have an array of size 5. Okay, the hash tables are not needed because you want the specific location to find this. Okay. Now, existence of an edge ij. What is the cost of finding whether there's an edge in edge ij in this list representation? Okay, just a minute here for you to think about that. Just like in the previous case, if you recall, for the matrix, we said that it's going to be yeah. So someone wrote E over N on average. That sounds right, but it's not exactly right because they don't have to have the same number of things like a hash table. So, but it's a reasonable guess. It's not E. In fact, if you're given the ith node, all you have to go is the length of the ith list. And so whatever that length is. So the existence of an edge ij can be done by order of length of list I. Whatever the length of that list I. Okay, so you have to go through that entire list to find out. Now we're going to develop another notion called in degree and out degree of a vertex. All right, and I think it'll become more clear as we discuss this idea. So in degree of a node is the number of edges coming into vertex V. For example, let me try to write the answer in terms of, so for instance, if you take this graph here, what is the in degree and the vertex? So let's put it like this. So we have vertices 1, 2, 3, 4. Some more space here. So we have vertices 1, 2, 3, 4, 5. And let's fill out the in degrees for each of these vertices. Now, for one, in degrees the number of edges coming into vertex V. So in this case, if you take vertex V, how many edges are coming into vertex V? Vertex 1, that's going to be 0 because nobody's coming into that. Vertex 2, there are 2 edges coming in. Actually 3, that's correct. So vertex 2, there are 3 edges coming into vertex 3. Vertex 2. Vertex 3, you have 2 edges coming in. All right, and the vertex 4, you have 1 edge coming in. And vertex 5, you have no edges coming in. All right, and the out degree is the number of nodes that are going out of the vertex. So for example, out degree of 1 is 3, because there are 3 vertices going out of vertex 1. And the out degree of 2 is going to be just 1. Only 1 vertex is going out of 2. That's 2, 3. Out degree of 3 is going to be 1, because you have 3, 2. And out degree of 4 is going to be, in fact, there's a loop here. So because of that out degree of 1, in fact, I'm just going to remove this loop. I'm sorry. Yeah, let's remove that. It's actually showed here. So we'll have to remove that too. So out degree of 4 is 0, because nobody's going out of 0, going out of 4. Out degree of 5 is 1. So there's 1 edge going out of 5, right? Okay. So out degree of 4 is 0, out degree of 5 is 1. Now, in fact, this idea we just discussed has been quite important. In fact, billionaires were made out of this idea. If you had this idea in the 90s, in fact, the Google was founded on this principle. Because the Google, think about these nodes as web pages. Suppose you have web page 1, web page 2, web page 3, web page 4, and web page 5. Now, web pages have links to other pages. So you might imagine web page 1 has link to web page 2, web page 4, and web page 3, and so on. Now, given this fact, let me ask you the question. If you think that this is a web where the nodes are the web pages, pages are the links from one web page to the other, who is the most important web page in this group? Okay, so someone said 1, someone said 2, someone said 1. Okay, so it looks like 1 is kind of winning this idea. Okay, do you think 1 is the most important web page here? Okay, so you're still thinking about this. Now think about this. Someone said 2. Now people are saying 2. That's good. I like that. In fact, I would claim that 2 is the most important web page because 2 has the most in degree. It has the in degree 3. Okay, in degree 3 means that most people have put a link to your web page. So if you are important, people are going to put a link to your web page. So in this web map, 2 has 3 links coming in. So 2 is important. Okay, so the most important thing is the in degree. So the highest in degree gives you the most important web page. Okay. Now let me ask you now a question. Now, if the graph is represented using adjacency matrix, and all the graph is represented using an adjacency list. Okay, to find the in-degree of a node, which graph, which representation is the most useful? If I want to find the in-degree of 2, which graph, which representation is the most important? Someone said adjacency matrix. That's correct. Because if I want to find the in-degree, that means how many people are coming into me. So 3, 4, 5, then 1, 2, 3, 4, 5. So can I also ask you how you would find the in-degree of a node using the matrix, if you say it's the adjacency matrix? So how do I, given the adjacency matrix? Very good. So someone said, how many ones in its column? That's correct. So all you have to do is to get the column sum. Okay, so if you can add the number of ones in a column, you could find the in-degree of a vertex. And that's the most important thing. What is the big O of that? Finding the big O of in-degree using adjacency matrix. It is n, because you have n things in the column. All you have to do is just add them up. What about if you want to find the in-degree using an adjacency list? That means you want to know how many are coming into the vertex 2, right? Because vertex, the in-degree is the most important thing. So do you think it's easier or harder to find the in-degree in an adjacency list? It's harder, correct. So it's harder to find it because in the adjacency list, you have to go through the list and every list here and look for places where you can find a 2. So if you want to know what the in-degree of 2 is, that you have to go through all of these things. That is going to cost you B amount of work, or N. Let's call it N. And then you have to go through every list because we don't know where this 2 is. So you have to go through every list. And so you have to spend N plus E time to do it. All right. Yeah, hash tables possible, but you have to be careful because it might affect other operations. So let's not just worry too much about that. Okay. So Google's original PageRank algorithm, which gives us great results, obviously it has changed quite a bit from the original idea, is the idea of in-degree. So it was the number of links coming into. So Google was able to go scan all the pages and find out, build the graph, because you could go to a page and you can grab all the links, and then you can build this graph. Because once you grab all the links, you get the list, and then you can figure out exactly the in-degree of a web page. Okay, so let's move on here. All right, I'm going to do a question here. The question is, let me start a poll here. The graph ABI here. Okay. So the question is, what is the order of growth of the memory used to represent a graph with V vertices and E edges using the adjacency list representation? All right. It looks like most of you are getting it, so I'm just going to move on. So the correct answer is E plus V. We just did that. Okay. So the next question is, what is the maximum number of edges? Let me start another poll. You can think about this. Find my icon here. Okay, start working on that problem. Okay, we want to know the maximum number of edges in a directed graph of n vertices. Is it n squared, n times n minus 1, or n times n plus 1? All right, so it looks like so far C is winning. B and C are tied here. Sort of pretty close. All right, I'll let you guys think about this just a little bit. Okay, so let me publish the polling results. Okay, so most of you said C. Most of you said C. In fact, it's easy to find out. Let's see that we have a graph of n nodes. If you take each edge, each vertex, if you take a vertex, from each vertex, you can draw an edge to every other vertex. And there are n minus 1 of them. So that means given any vertex, you can draw n minus 1 edges. Since you have n vertices, so you can draw n times n minus 1 edges. So that's the correct answer. Okay, so here's another problem. Suppose in this case, the graph became undirected. Now what's the answer? I will give you the answer because I think let's not spend too much time on it. Now, if it's an undirected graph, then I will not be able to count two things for each node. I can only count one. In the previous one, I was able to count two. But so the answer is going to be this, because it's going to be exactly half of that. You can only count one between two edges because it's undirected. There's no arrow between the two. So I can only count one. All right. And you can actually see that easily if you have, let's say, 3 nodes. So suppose n equals 3, then you have 3 times 3 minus 1 over 2, which gives you 3. And that's how many edges you have in this undirected graph. Okay, moving on. A few definitions. We call something a simple graph if there are no self-loops. That means that cannot exist. No self-loops. So, so it's a simple graph. For any two nodes, there's at most one edge per direction. In other words, you can only have just a simple edge here. Now, undirected graphs are represented by symmetric matrices. What we mean by symmetric matrices is if you take something like this, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we have 1 to 2 and 2 to 1 are non-zero. And then 1, 3 and 3, 1 are ones or true. Okay, 1, 0. Actually, this has a 0 too. I didn't write the 0, so I missed the 0. But anyway, so the idea is that they're called symmetric because in the matrix sense, we have A of ij is A of ji for every j and every I. So when you have an undirected graph, it's always represented by a symmetric matrix. A directed graph obviously doesn't have to be symmetric. This matrix is not symmetric because you might have an edge from A to B, but not one from B to A, not necessarily. Okay, so directed graphs don't have to be symmetric matrices. Okay, there are 4 types of graphs. One called undirected, unweighted. So let's say we have nodes 1, 2, 3. So this is an undirected, and there are no weights. And then you can have undirected, but you can have weights between them. So that's an undirected weighted graph. Or you can have a directed and unweighted graph. So that's directed and unweighted graph. So unweighted graphs are essentially saying there's an edge. It's true. There's a flight from 1 to 2, for example. Or you could have directed and weighted. So that's a directed and weighted. So typically when you represent these things, you can represent them by matrices with true for unweighted, okay, true for unweighted edges, but false for weights that don't exist. Otherwise, you can just put the number in there. Okay. Okay, next we're going to define what's called a path. Path is a sequence of nodes. A path is a sequence of nodes. And hold on, let me see. Let me get my okay. So path is a sequence of nodes such that each node has an edge to the next node in the sequence. So you could take a path from here to here. So A to D. So the path from A to D would be A to C, C to E, and E to D. And each of the legs in this path has a weight. And we can say the path length is the total weights. Okay, we call something is a cycle if it's a path of greater than or to 2 that starts and ends in the same place. For example, I think you can have paths in directed graphs, or you can have paths in undirected graphs. I mean, cycles. Can you write down the cycles in this graph? There are many cycles in this graph, but there are a number of them. So it's undirected. So you can have a cycle A, H, G, A. Notice that the cycle always starts and ends in the same node. Now, clearly, if I put arrows here, then it's going to restrict me on finding cycles. I won't be able to find cycles freely. So once I put the arrows, I can get another cycle. When you talk about a cycle, you cannot have the same edge twice in the cycle. Okay, could you write a cycle, another cycle? One cycle is A to H, H to D, G, and G to A. Could you write another cycle in this graph? Okay, someone says CDEC. See, oops, I need to put some arrows here. Yeah, if I put the arrow CDEC, that would be fine. I didn't put all the arrows in all of them. Okay, so now I have, they're all directed. So yes, that's correct. So with this one, I can say CDEC is a cycle. And also you can have a cycle BDFE CB is a cycle. Okay, so that seems to me the longest cycle, but you could find other cycles there. Okay, so now the next question is, how do you find cycles in a graph? What is the algorithm for doing this? So let's talk about that a little bit. Okay, I'm going to skip this just for now a little bit here. Okay, so the algorithm for finding cycles is called depth first search, or we call it DFS, finding a cycle. And the so depth first search, let's take an example. So let's say that we have a graph. I'm just going to draw a graph here. So let's make it a directed graph. Now clearly, 1, 2, 3, 4, 5 is a cycle. I can introduce other nodes if I like. Okay. So the way this algorithm is going to work is it's called the depth first search. That means you go as deep as you want, you can go until you cannot go any further. So for example, I can start from node 1. I can start from node 1. And then I can go from node 1 to node 2. Because I will know from my adjacency list or adjacency matrix that I have an edge from 1 to 2. So when I go to 2, I will look around to see where can I go from 2. From the adjacency list, I might say, well, I can go to 3 from there. And then from 3, I will look around and see if I can, where I can go from 3, I can go to 4. In fact, if you draw the adjacency list representation of this, it might become more clear. So we have a node from 1 to 2, and then we have a node from 2 to 3. We have an edge from 3 to 4. And we have an edge from 4 to 5. We have an edge from 5 to 1. So that's the adjacency list that represent this graph. It's a very simple graph, just as one cycle. All right, so you might imagine when I'm trying to find the cycle, I might have to go through, I go to 1 and see where I can go. I can go to 2, then from 2, I can go to 3, and so on. It doesn't happen like that always because graphs are not this nice. And therefore, you might have to do more work to kind of figure this out. So that's why it's called the depth first search. So the depth first search idea is the following. I can demonstrate this with the thing we discuss called like let's say we take a graph. Take a graph like this. All right, so let's say these are named 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 vertices in this graph. And what we're going to do is we're going to see if there's a cycle from 1 to 1. Or we're going to do depth first search to find this. So basically what you can do is you can say, okay, we're going to take the node 1 and see where we can go. And you can choose any place to go. Like, for example, because I know 1 is connected to, let's assume that these are directed edges, so this way the less confusion, I guess. Okay. All right, so if you look at 1, I can go to either 2 or 8. So I can choose either one. I don't know which one I should choose to get to the best path, but I have no idea. But let's suppose that I chose 8. But if I chose 8, I get stuck because once I go to 8, 8 is like a sink. There's nothing going out of 8. So that means I have to backtrack and then try the other path. And I go to 2. Now from 2, I have 2 places I can go. I can either go to 7 or I can go to 3. Let's suppose that I chose to go to 7 because there's a link and I have no idea whether going through 3 or 7 is the best way to go. Let's suppose I go to 7. When I go to 7, I have 2 choices. I can either go to 4 or I can go to 6. Let's suppose that I choose to go to 6. But if I choose to go to 6, I cannot go anywhere from 6. So therefore, I'm stuck. So I need to backtrack and try the other route, which is 4. And from 4, I can go to 5. From 5, I can go to 6. I mean, from 5, I can go to 1. That means I found the cycle. All right. So what data structure can I use to do this, to do the depth first search? It is a stack. That's correct. Okay. So if you recall, we at some point we talked about finding a path through a maze. Essentially, that's a depth first search that you're doing. If you have a maze, if you're going to traverse through a maze, you can think of a maze as a graph. So if you think of a maze could be a graph that are connected to, the rooms are connected in ways, right? So you could have a graph. I mean, it's an undirected graph. Essentially, you take a maze like this, and you can connect something. So that means there are paths from that to the other. So there's a maze. All right. So all you need is a stack. So you keep elements in a stack. The idea is you go as deep as you can, and then you backtrack when you cannot go no more. And that's called the depth first search. Okay. The remaining time, what I like to do is, I want to go through the questions today because you have an exam coming up. I want to kind of remind you about the exam. So for the exam, you have to look at PS6 and PS7. An exam will cover BST and Avl trees. All right. And let's ask you a question. What's the maximum nodes in a BST with height h? So let's say we take a BST like this. Maximum nodes means that they are all full. The height is the number of edges from top to the bottom. And in the level 0, you have 2 to the 0 vertices. Level 1, you have 2 to the 1 vertices. Level 2, you have 2 to the 2 vertices. So for this tree, the height is 2. And you can see that the maximum number of vertices that are in a tree of height h would be 2 to the 0 plus 2 to the 1 plus 2 squared. The last level always have 2 to the h. Notice that it's 2 here and 2 to the h. Now it turns out that this is equal to 2 to the h plus 1 minus 1. And what is the minimum number of nodes in a BST of height h? Okay, it's h plus 1. That's correct. So the minimum would be this worst case scenario where you have the height h. That means the number of edges is h. The number of nodes is 1 more than that. So the minimum is h plus 1. The maximum is 2h plus 1 minus 1. Now, let's do some code, because you may have to write code in your test. Let's look at the code with this particular thing. You can try to write yourself the code for finding the minimum node in a BST. Now, one thing we know is that when you have a BST like this, so that's a BST. Where is the minimum node? That's the root. Where is the minimum node? Minimum value node. The leftmost node. So that's the node you want. So that means you have to keep going left, starting with the root. Just keep going left until you cannot go left anymore. All right. So the best way to write this code is to make sure that if the root is null, that means you don't have a tree. Okay. Return some. That means it doesn't exist, right? Because there's no minimum. Okay. Otherwise, what we're going to do is while the root dot next is not null, we go root is assigned root dot next. All right. And so what you're doing is you keep root dot left. Next, that's not right, because we're looking at a BST or binary tree. So we have to go left because each node has 2 pointers, left and right. Okay. And then when you leave this means root dot left is null. That means your root is the last one here. Okay, root has come here, and that you found root dot left is null. So that means you just have to return the root dot value. All right, so that finds the minimum of this tree. So the next question is write a recursive function to find the height of a binary tree. So I'm going to define the height of a tree as -1 if t is empty. Otherwise, it's going to be 1 plus the max of the height of the left subtree and height of the right subtree. So that's the definition of the height. So if you keep that in mind, I'm just going to scroll down a little bit here. Or maybe I'll see if I can pull this down here. Okay, so let's convert this to some recursive code. So this code says that if root is null, return -1. Okay, otherwise, you can return 1 plus math.max height of, you're calling the same function, it's recursively calling it root.left and height root.right. That's it. All right, so 1 second here. Yes, so this is fine. Okay, there are other ways to do it, but I'm just showing you one way to do it. So this is finding the height of a binary tree. Okay, notice that it's a binary tree, so it doesn't even have to be a BST, but it would be the same for BST. Okay, I'll save these notes, so don't worry too much about it if I'm going too fast. Count the total number of nodes in a binary tree. So if you want to count the nodes in a binary tree, the count of the nodes in a binary tree, it's equal to 0 if t is empty. Okay, let's call this C of t. Count of t is 0 if t is empty. Otherwise, count of t is going to be 1 plus the count of the left and the count of the right. So converting that to a piece of code, essentially what we're saying is either it's 0 because we define a tree recursively. So here's my t left, here's my t right. So if it's empty, there's no count. If it's not empty, then you have 1 plus, which is the root, plus however many elements in the left and however many elements in the right. So converting this to code, you can say if root is null, then return 0. All right. Else you could return 1 plus nodes are of t dot root dot left plus nodes are root dot right. All right, that's it. And that's the so most of the code that you have to write in the exam or something is going to be fairly trivial. It's short. I wouldn't say trivial, but it's short code. Okay, and then let's suppose that you want to find a target in a binary tree. If you're going to find a target in a binary, notice that I'm doing things with a binary tree, not with a BST. But the only difference between a binary tree and a BST is that the BST has an order. So if you ask me where some element is, where a target is, I know how to go find that because I keep go left or right, depending on where things are. But if you try to find a target in a binary tree which has no order, okay, I'm doing things with no order for you to think about the things with order. This means that you have to traverse because you have no idea where the element is. Oops, what happened here? So we're gonna have to go through every element in this tree because we have no idea where this thing is. All right. So how do you go through every element in a tree? Just 1 minute to answer that question. Yeah, you could do like an Inorder Traversal. So the Inorder Traversal is given as left, root, right. So that's called the Inorder Traversal. So what we can do is we can just say if the root is not null, right? We have to do a few things. One is that we will go to the left, root dot left, and target. We have to carry the target with us. And if the root dot value, that's the root you're looking at, is equal to the target, we return true. All right, or you can return target whatever you want. And then you're going to go to the root.right. This is going to the right tree with the same target. All right, so the lesson I'm trying to convey here is that if you have to look around the tree, say, for example, someone is asking you to, even given a binary search tree. So they're saying, well, given a binary search tree, can you find all the values between 5 and 55? So what are the values that are in the binary tree that are between 5 and 55? So in this case, you have to do two searches. One is that you got to go through the binary search tree and find 5. 5 could be there. And the 55 could be here. 55 can be in the other tree. So you will find those two things. That means now you have to traverse, you have to do some kind of order traversal between 5. So you have to think about what are the elements that are bigger than 5 but less than 55, right? Those elements are the elements, because we know the 5 is small, so the bigger elements, bigger than 5, are these elements. That's bigger than 5. And this is bigger than 5. And those are the elements. So you're really looking for elements that are between 5 and 55. So in order to do that, you have to do a traversal between the starting place and the end place. So if you do the in-order traversal from node 5 to node 55, you might be able to find all the nodes in that range. So that's an operation on binary trees. Okay, finally, let's talk about the Avl trees, since you're going to get a problem from that. This one says that build an Avl tree from the nodes 1, 2. Let me recall you that there are a few things you need to know about Avl trees. So if you have a shape like this, clearly that's not an Avl tree. And what we know is the order of these the elements are going to be C is the smallest, B is the next smallest, and A is the largest in this tree. It's a BST. So in this case, we do a right rotation to give us a B and A and C. Now, if you do an in-order traversal on this tree, you still get CBA. That's the order of the thing. The same with this one. If you have A, B, C, in this case, A is the smallest, B is the second smallest, C is the largest. In this case, you do a rotation, you will get B, A, C. The third case is that you have A, B, C. Now, the way we fix this tree, now we know the order of this tree is that B is less than A, but C is bigger than B, right? So the smallest one is B here, and then C and A. So that's the order of the elements. Now in this case, you have to do two rotations. One, you do a left rotation around the child. So you get A and C and B, and then you do a right rotation to get C, A, and B. All right. And so notice that still the same order is, so so let's try to quickly build this thing since we have only 10 minutes. So I'm going to put 1. That's okay. 2 goes here. That's still okay. Now I have 1, 2, 3. I will have to do a rotation to get this. And then I put 4, and still okay. Again, how do we know it's okay? Because you compute the balance factors. So as long as the balance factor for any node, which is the difference between left and right trees, is less than or equal to 1, you're going to be okay. So once I put the next entry, all right, so balance factor of one of the nodes is going to be broken. Which node is that? Yes, it is 3. Okay, so the balance factor of 3 is broken. And therefore, you have to do, if you look at the shape, you have to do a rotation like this. So you will get 2, 1, and then you will get 4, and 3, and 5. All right, so we have that. So now let's insert 6 into the tree. So right now it's an AVL tree because you can compute the balance factor for all of these things, and you will find out that's an AVL tree. So if you insert 6 into this tree, you're going to get this. Now, where's the balance factor broken in this case? The 2. Okay, the balance factor for 4 and 5 and 3 and 6 are all fine. 2 is the one that's broken. Okay, so we will have to do a rotation, right? We'll have to do a rotation. The 2 is broken because of the right-leaning thing. Who is going to be the root if I do a rotation? Okay, 4. Let's say 4. Suppose we do a right rotation here. So the 4 comes here, and then 2 and 1. And then you have 5 and 6 are still attached to it. And the only difference is that the 3 is going to go there. So that's how you get that. Okay, so the 4 becomes that. And clearly this is an AVL tree because the balance factor for is that. So left and right rotations, if you think about the number of statements needed to implement one of these rotations, left rotation and right rotation, we talked about those things. Now, when you do a left rotation, you essentially, so for example, the reason you do a left rotation is that maybe this is quite large here. Okay, maybe one way to think about that is maybe you have like something like this, so you will try to do a left rotation. So when you do a left rotation, then the depth reduces. Right rotation, the same idea. So how many statements are needed to implement a rotation? Like if you write the code to implement a left rotation or right rotation, how many pointers do you manipulate? 3 pointers. So someone said 3 pointers. Someone said 4. Right. I think I will ask you to take a look at the nodes we did. It's you can manipulate. You have to manipulate a root at least 2, but 3 is the number there. Okay. So you need 3 statements to really get this thing going for each rotation. So what that means is every rotation is a constant time operation. 3 rotations. Go back and look at the nodes that we did. We did a nice picture and showed you how it's done. Okay. All right. I'm going to stop here and let you ask questions if you have any questions about the exam. No, you don't need to write AVL code. You have to write some code, but not the code that we've already done. Okay. Do we need to delete a node in the AVL? That's possible. Again, you have to know how to delete a node in an AVL. I think it's more important to know how to delete a node. If you recall the deleting the node, if you're trying to delete a node in a BST, what we did was just get this thing out here. So if you're going to delete, let's say, this node, right? Let's call this 1, 2, 3, 4, 5, 6, 7. Let's suppose I want to delete node number 1. What is the right, how do we do that? For example, I have to find a replacement for one of the root nodes. Okay, so the replacement for 1 could be anything that's closer to 1. For example, 6 or this, okay? If that's node number 4, I guess. Right, so those are the two things that can replace. So what I can do is I can swap these two nodes and then just delete that. Because either one of those nodes is going to be okay. Yeah, you have to, it's mostly BST. The exam is 2 hours long. And you also have to create a Gradescope account. Is it going to be like this? Well, I think again, I did some casual kind of problems, but I think this should give you an idea. The best thing to do is you should go and look at the problem set. I think I mentioned 6 and 7, I believe. Problem set 6 and 7 are the key things. So if you pay attention to 6 and 7, 6 and 7, BST and Avl trees, that can give you some idea there. The difficulty of the problems in the exam are quite similar to exam 1. You should wait for the instructions, whether you can look at problem set 6 and 7 to answer the exam or not. We haven't written those instructions, but you will get the instructions once we agree on that, you will get those instructions. So just follow the instructions. If you're not supposed to look at them, don't look at them. Open note, yeah, I emailed, that's correct. I think on the announcements, it says open note. So some ways you can interpret that as, but just wait for the instructions anyway. I'm good. Only thing, my internet didn't work well, so I lost 5-10 minutes. Sorry about that. It's just, this is why I don't like teaching online. It's just not fun at all. I feel like I'm talking to a computer. I see you guys typing things, but it's not you. It's some text that's coming to me. Yeah, so I think you should really, again, just go through your notes and things that we have done in the class. And, because you have only 2 hours once you start the test, you have only 2 hours to complete it. So there's a time pressure for you, even if it's open notes. So it might be a good idea to just look at them beforehand, before you start the test, and make sure that you know how to find the answer, even if it's open note. You know where the things are. you are uploading your solutions to Gradescope, and Gradescope. Some of you may have used Gradescope in 1.11, I think, and TAs, the graders will grade that, and you will get the questions, the responses on Gradescope. Test post on the problem set page. Again, I think wait for the email. There will be an email that's coming on Sunday, so you know when to start. And all the so you should check your email. Make sure you check your email on Sunday. Really important, I think. Don't miss the test. Again, all the instructions will be on the email, so I'll just say that you know, just whatever the time that was allocated for the test before the coronavirus came is probably what it's going to be. But again, wait for the instruction. These things can change because you know things are very fluid at the moment. Construct the BSTs. Yeah, I think you should know how to construct a BST, or you know, you should know how to compute the number of operations for constructing a BST, things like that. For example, if you construct a BST from a number of elements, you should be able to figure out how many comparisons were made to build that BST. Okay, so I think since it doesn't seem like more questions are coming in, let's call it a day, and let's. Would you like to have any kind of office hours on Saturday? Okay. So I will send you some. I'll send you an email about. I gotta look at my schedule and send you an email. I think if we do office hours, you might want to bring questions, and then we can go over those things. But let me just make sure that I have the schedule open for me to do it. All right, so I think I'll sign off, and good night. See you next week, or maybe Saturday. Who knows? Yeah, thanks. Bye-bye.